In this module, we are going to start talking about second law of thermodynamics. So, this is pretty exciting because we have finished the first law of thermodynamics, in which we have seen energy energy is conserved, and we have seen how different forms of energy go from like one form to another form, how one form of energy goes to like from work to heat and heat to internal energy and things like that. So, only thing that was not answered in the first law of thermodynamics is that whether the change will be allowed or not, whether a conversion of heat to work will be allowed or not, or whether this conversion will be fully used or not. So, second law of thermodynamics is going to add a new thing, a new rule to the change of matter or change of different forms of energy, and that is what we are going to learn in this particular modules, which is going to go on like now for several modules. We have divided into in two parts. In the first part we are going to deal with the classical approach to second law of thermodynamics, which is typically taught in undergraduate courses. However, since more and more books are coming up with molecular approaches, that means they are trying to understand this laws of nature from atoms and molecules. We are also going to adopt the molecular thermodynamics approach to complement our understanding of second law of thermodynamics and in general thermodynamics. So, thermodynamics basically is like second law of thermodynamics is everything in thermodynamics itself, as you will see. Once we understand that, we can get all other forms, all other laws as a corollary to this one. However, of course, we have mentioned the zeroth law of thermodynamics as a foundation to the second law, because we had to define the temperature using zeroth law of thermodynamics. Similarly, first law of thermodynamics, which talks about conservation of energy, that is already is known from other fields as well. However, the second law of thermodynamics, as you will see, is unique, and it will give us a handle to understand when one thing will actually change from one form to another form. Before we start that, I am going to start with some quotations for the second law of thermodynamics, as people have mentioned, the great scientists have mentioned over the time. The first one is by Albert Einstein, who says that the classical thermodynamics is the only physical theory of universal content, which I am convinced that within the applicability of its basic concepts will never be overthrown. That means, we have seen that time and again that there is a theory which is proposed, and then of course, that is modified or made better and things like that over the time, right. For example, Newtonian equations of motions, we now know that that is only an approximations to underlying quantum mechanical concepts. So, however, he says that the thermodynamics is such thing that pretty much will be solid and is not going to be overthrown for a long time. Second one, second law of thermodynamics has the same degree of truth as the statement that if you throw a tumblerful of water into the sea, you cannot get the same tumblerful of water out again, by James Clerk Maxwell. What does it mean? So, you take a bucket of water, let us say you specify in that bucket all the water molecules, you number them or you color them, let us say, you tag them by somehow and put it into sea and try to collect back the same. You can do the same, you can you can take a colored water, a mug of colored water, put it somewhere, a pond or something, and try to get back all the colored molecules that you have. Will you get back ever? So, if you cannot get back ever that thing, the truthfulness in that, in the fact that you cannot get it back, is of the same degree of truthfulness as the second law of thermodynamics. So, if you cannot get it back, and if you agree that you cannot get it back, then you are basically agreeing to the fact that second law of thermodynamics holds. Okay. Third one, heat energy of uniform temperature is the ultimate fate of all energy. So, we talked about energy conservation, energy to work, work to heat, heat to energy and all sorts of things, energy to energy, solar energy to chemical energy to other energies. We talked about all that, right. But then where we are heading? We are heading towards a direction where everything will be heat energy, and the power of sunlight and coal, electric power, water power, winds, tides do the work of the world. They do, lots of work. We use solar energy to do work, we use electrical power to do work, water power to do work. We have shown some examples of that during our demonstrations. And in the end, all unite to hasten the merry molecular dance. So, the merry molecular dance meaning the jiggling and wiggling of atoms and molecules under the heat or temperature that is there. So, basically everything is going to go, all the energy that we talk about, whether it is energy of the sunlight or we do the work or whatever, we eat food, at the end everything is going to go into heat energy, and it is just going to just change the motions of the molecules at the end. That is the fate of all energy. That is what he talks about. This is very interesting. I put it there because it has been suggested that thermodynamic irreversibility is due to the cosmological expansion. Now, again, these are the quotations from different people. You may not be able to connect it right now, but at the end of the course or at the end of our discussion of the second law of thermodynamics, you will understand all of that. So, what it means is that the fact that that people believe that we are now in the expansion phase of the universe. There are theories, right, they said that universe will expand and contract, and there are many different theories available. But this is I think the theory by Roger Penrose or Stephen Hawking that says that it will be expand and then contract. So, right now we are in the expansion phase, cosmological expansion, and the fact that we see things irreversible, things that we see that that happen irreversibly due to this expansion. And this is from George Potter's video, which was BBC lecture series in 1967. He also has a very nice half an hour video on the thermodynamics, this thing. I suggest all of you to see that. And there he mentions that it is a sine qua non of scientific enlightenment. That means it is absolutely necessary knowledge for any scientific understanding that one might have, be it like biology, chemistry, physics. In every subject you will find that the application of thermodynamics will be essential, or especially the second law of thermodynamics. In order to understand what is second law of thermodynamics, we are going to talk about some changes. So, as we said before, that thermodynamics gives us the rule to say that whether the change will take place or not, whether it is a change of matter, change of phase, change of state, change of anything for that matter. Whether that will happen or not, that depends on the rules that is governed by the thermodynamical principles. So, we are going to talk about few of the changes. One change is that the gas expands spontaneously in the vacuum, right. Like if you let us say you put gas in a container, try to give some color to that and then open the container, how do you expect the gas will expand? So, therefore, it is a natural process, we see that every day and does not bother us. Even a child sees that, it does not bother the child, that why it happens, right. It is quite natural because we see that every day around us. Maybe you do not understand that, but for example, you light an incense and what happens, the smoke that comes out, it will fill the room. It is quite natural for us to see that. That is a spontaneous change that we observe. Let us talk about one more. Heat transfers from hot to cold, we see that always. Even in our class 7 standard experiment, I think I remember that we had to show that heat transfers to a metal or something, and then we put wax on one side of the metal and heat the other side. So, that side will be hot, the work side will be cold and the works will melt, which means the heat transfers from hot to cold. It is quite natural that when you put your hand in a boiling water, you feel hot, because the heat transfers from boiling water to your hand. Similarly, because you are of course you are colder than the boiling water, and you will touch an ice, you are hotter than the ice, therefore the heat will transfer from your body to the ice, and therefore you will feel a sensation of cold. So heat transfer from hot to cold is quite natural phenomena for us to observe. However, we have seen that we have a refrigerator in our house where the temperature of the refrigerator is colder than that of the room. So there the heat actually transforms from cold to hot. We will discuss that, why that happens. That is not a spontaneous change. So we are talking about only spontaneous changes, spontaneously heat transfer from hot to cold. Hot to cold, again in terms of temperature, hot is higher temperature, cold is lower temperature. Sometimes some ordered processes, as such as formation of crystals, crystals from saturated solution also happens. So we can see an order. For example, we see that trees grow, right. This is an ordered process. We see many ordered processes around us. So it is not that only we see that something that spontaneously happen will go to some disordered or chaotic nature. Many things, for example, when we build a house or a tree grows, or cells actually combine together in organized form, making an organisms, they are all ordered processes. Those ordered processes may tell us that it is spontaneously happening, and therefore it might be going against the natural process. However, there are things that are around that which will be getting more of disordered nature. For example, stretch rubber, we will show you a demonstration, very simple one. So when you stretch it, it is not a spontaneous process, you have to really do the work, right. However, when you release it, it is a spontaneously shrinks. It does not shrink beyond this, it will shrink to a particular optimum length, it will not go below that. So a stretched rubber shrinks and cools down. Now you try this. You have this balloon, you stretch it, first you touch it here, you see the temperature, or your forehead also is fine. Stretch it, touch it, release it and touch it. You can try that, and you will see that when it spontaneously comes back, it will get cooled down. When you stretch it, it will get heated up and spontaneously cool down. Another thing you can do here is that you can put it in your finger, stretch it, this works very well, release it, you will see that your fingertip becomes colder. So this is a very standard experiment, and what you are going to learn later is that it is a demonstrations of entropic elasticity. It is getting cooler, the reason again we will explain later, but again here what we are talking about is that a spontaneous process of an extended rubber to a normal form, that is a spontaneous process that happens. A ball bounces to the ground a few times before stopping completely, and opposite never happens. So you are going to drop the ball, this is very natural for us to see that, right, and nobody is going to associate like initially any theories behind it. You say okay, gravitational attraction, therefore it is falling down. I understand that gravitational attraction leads it to fall down to the ground. However, the energy of this particular ball remains conserved, right, because initially it is the full potential energy gets converted to kinetic energy. When it touches the ground, it has the highest kinetic energy, and therefore it can bounce back, should bounce back to same level, right, but it does not. So the first law of thermodynamics does not prohibit it to not come back to our hand. Neither any rule of physics will tell you that why it should not come back. It is perfectly reversible process that it goes down and comes back to your hand. There is no problem associated with that. Yet we do not find that thing comes back to our hand, and we call that an inelastic collision, right. If you ask them okay, why it does not happen, you said inelastic collision. What does it mean? What does an inelastic collision means, and why these processes are inelastic? What is the nature of this thing that makes it inelastic? So we will talk about that later. So, the point is that it is not that the fact that it does not come back has anything to do with forces. So, force that pulls the ball will have exact and opposite forces when it hits the floor, and therefore, it should have come back to our hand. However, it does not come back because we know that what happens, there is a loss in the energy, and how that loss happens and why that loss happens, that is what we are going to talk about when we discuss about second law in more detail. So, in all the processes mentioned above, the energy is conserved, as I said, and our experiment can be made in such a way that energy remains conserved, yet the opposite process never happens and this process only happens. This non-conserved quantity. So, in every this irreversible processes, which means when I talked about expansion of gas is an irreversible process, I talked about the ball falls down to the ground and it does not come back, that is an irreversible process, and we have given some other examples. In every case there is energy is always conserved in all those cases, right, like that never changes, because we had that potential energy got converted to kinetic energy, then some of that got converted to sound energy and then heat energy and all that. So, energy is always conserved. However, some quantity is non-conserved, that is non-conserved when we are holding the ball versus now when the ball is again static on the ground. There is something which is entropy that has increased in this process. This non-conserved quantity is called entropy, and second law of thermodynamics says that entropy of the system, whatever system we have discussed about system and surrounding, right, entropy of the system plus surrounding always increases for a process. Remember our discussion about system and surrounding. System was whatever we talk about, let us say ball, and surrounding will be everything else in the universe except the ball. So, when we talk about system and surroundings, we are talking about the entire universe, So, when we are holding the ball versus now, entropy of the universe has increased. In fact, when we started the class and now the entropy of the universe has increased. In fact, at every moment, at every second, every minute, entropy of the universe is increasing. So, entropy becomes maximum when the system reaches equilibrium, and we call that as an equilibrium system. So, what is that entropy? So, we have said that there is a non-conserved quantity. Unlike all physical laws, things are conserved, forces are balanced, energy total energy is conserved, but entropy is this non-conserved quantity, and what is that? That is what we are going to study, right. So, it is normally said to be an ordered to disordered motions. So, I had the ball, dropped it, and it bounced it back few times, right, it bounced back few times, each time the height was lesser and lesser, and then it stopped, and you see when it hit the ground, what is there on the ground? The particles, atoms of the ground. When it hit that, it transfers some energy to the ground particle, and then it came back, again hit the ground, again it transfers some energy to the ground particle. Now, when it hits the particle on the ground, the atoms of the surface of the floor, that energy again transferred to the next atom, to the next atom, to the next atom, and gets lost. It is like again putting water into the sea. Once you put it, you can no longer get back. Why? Because those water molecules now has gone into and mixed with the sea. Unless they come back together and to your hand, it will not happen that it will get back the same thing, right. So, this is taken from Atkins, these two pictures you see here. So, initially the there are random motions. So, when the ball is falling down, it has all the atoms of the ball is in the direction of the downwards direction. Once it hits that, then it gets all oriented differently, unless it come back all together, unless this the dissipation that has happened to the atoms of the floor, it comes back together, you are not going to get back the ball. If they decide that okay, let us all the energy that we have been dissipated to the atoms of the floor come back in harmony together and pushes the ball back, then it will come to our hand. But the probability of that happening is extremely small. So now we are going to show some demonstration and see. Okay, so now this is the ball falling to the ground and all that is very common to us, right? You know, I can put a glass and it will break. We do not see the opposite process happen. An egg breaking is very common phenomena. Opposite never happens. Do you imagine that a broken egg will, you know, combine together and come to your hand? Never, right? However, in our real world it never happens. But we can always make that thing happening in a virtual world. How? We can always take a movie of that and run it backward, right? Then we can see the egg coming to our hand, right? But then you will know for sure that that is surely a movie running backward, isn't it? You know for sure that it is moving running backward. You know for sure that that cannot happen in the real world. So here we are going to show you some movies and you have to tell that whether they are these movies are running forward or backward. Okay? So let us see if it runs here. So what happened, the air that was there inside the outside suddenly came into the balloon and swollen up the balloon. You see, saw what happened? Swollen up the balloon. They, you know, some air molecules decided to come inside the balloon and swell it up. Can it happen in the real world? Okay. So in this there was a ink which is there in the water suddenly decides to coagulate together and come to the hand. Possible? This is interesting where I do not know how to, yeah. So I will run that again. So it starts all that, you know, all these pens, they were like all scattered and they decide to come back and form a very nice arrangement. Not possible, right? You are sure about that, right? Fourth one, this is a mixture of red and blue particles and they are suddenly unmixed. Possible? No. Now Raymond is in the swing. Tell me whether the movie is running forward or backward. We will play it once more. Is the movie running forward or backward? Okay, one more. There is a pen here which Raymond is trying to, you know, swing it, and here it is. Is it running forward or backward? Now we see suddenly that we cannot answer this, right? It is difficult, it is not obvious what has happened. If you take my picture walking on the dais like this and run it backward, will you be able to tell whether the movie is running backward or forward? If I take a movie and then run backward, will you be able to tell? Sure? Try that. Try that. You take the movie and run it backward. Do it yourself and see whether you can tell that whether running forward or backward. If I drink the water very slowly, I will drink it. I cannot spill it, huh? Forget about the spilling. Of course, you can see that because here the water will be going out of the bottle, right. So, I will not do that. Let us try that. This one you will be able to see I am drinking our movie running forward backward, but this one run it backward and you will see whether you can tell whether forward or backward or not. If you do not see the water spilling from the bottle, and if I do it slow enough, you will not be able to tell. Now, why is that? Why in one case we could tell, in another case we could not tell? Either the movie is running forward or backward. We don't. I did not tell you which is that one, but you are unable to decide. Now, why is that? To understand that, again we have to understand the arrow of time. So, as I told you before that entropy increase is a spontaneous process. So, anything that is happening spontaneously increases the entropy. So, if you see that something is not possible, entropy must be decreasing in that, and if you see that you cannot decide, then the system is in equilibrium and entropy is not increasing. Because entropy is not increasing, you do not know whether the movie is running forward or backward, because if the entropy would be decreasing, then you will know for sure that the movie is running backward. In both those two examples, the movie were running backward, but you did not guess it, right, obviously. So, those are examples of an equilibrium processes, and at that process change of entropy is 0. Of course, I do not claim that it will be exactly 0, but we try to make it as close to 0 as possible. It is not detectable by our understanding at least. So, what does that mean? It means that at every instant, as I told before, at every instant, every point of time, entropy must be increasing for all irreversible processes. All the reversible processes, entropy is not increasing, but all irreversible process, whether it is breaking of an egg or water falling from high to low, and all other processes, you can name it, a chemical reactions, a spontaneous process, every process entropy is increasing, entropy of the universe is increasing. And since the decrease is never possible, which means that we can associate the entropy with the arrow of time. So, let us say we are here today. So, this is like 2018, right, which means it is higher than 2017, 16, and we are going back and back and back to 0 and BC and all that, right. So, where then at some point it must have started, right. So, at some point we could not go back further, and that is our 0 of time. So, every year if you look backward in our past, entropy must have been, entropy of the universe must have been lower than what is today, right, because every process is irreversible process is contributing to it, which means that it will go back and back and back, and at some point you cannot go back any further, and that is the origin of the time, because time starts from 0, it does not have negative value. So, the 0 of time is, as we understand, we can say that the 0 of the time is the Big Bang, and then with time entropy of the universe kept on increasing till today, which is here, and that is what I drew here today. So, this is today, and I put a linear line, but just a schematic line. I do not know whether this change is linear or not, it may not be linear, it may be like exponential or super exponential, we do not know that, at least I do not know that, but it must be increasing, it is a monotonically increasing function of time. So, therefore, entropy is used as the arrow of time, quite naturally, because we know that at some point in in the past entropy must have been 0, and that is associated with that time when the universe was just like a point, and then the expansion happened, and then current universe we have with entropy, and it is still increasing. And the reason that it is increasing, can you tell me the reason that it is increasing? Why is entropy still increasing from whatever we discussed till now? Can you predict that why it is still increasing?
Because it hasn't grown to its equilibrium state.
Correct. So it has not reached the equilibrium. If it reached equilibrium, entropy would not be increasing, and we will not see any change anymore. Okay. So that is the beauty of it, that our universe is not in an equilibrium situation, because it is still expanding, it is expanding faster, and we know that our entropy is also increasing. So therefore that cosmological expansion thing came into the picture, that because probably this expansion is related to all those spontaneous processes having to do with the increase in entropy. Now we know that entropy is increasing, so it was lower before, right now it is higher, but where it will end then? It will keep on growing, right? So 2018 it is some value, then 2019 will be higher, 20 it will be even higher, and let us say 3000 or 4000 some time it will be very high, right? But we know the lower value 0. Do we know the higher value? We do not know the higher value, but we know what will have its higher value. The fate of the universe, I mean the future, we can predict, right? We can predict that the entropy will be very high, so high that no more changes will be possible, and we know that again another quotation, that everything will go to merry molecular dance, in which all forms of energy will convert to heat energy at a constant temperature. That means there will be no longer structures available. As long as we have structure, we have energy in a very close form. It is not dissipated. You will learn later on that as long as you confine energy to a particular place, your entropy is low. Entropy will be high when it will be distributed, spreaded. So as long as you see structures in the form of either building or trees or any organizations having to do with the lower value of entropy. So highest value of entropy is such that there will be no structure, no organizations, that means no human being, no planets, no other thing. It will be just a heat bath in which nothing will exist, and that is the fate of the universe. So now the beginning of second law of thermodynamics had to do with people's idea to make an engine with better efficiency. So we talked about history of thermodynamics, and there we saw that around 1770 years sometime we got steam engine, and then around so people were trying to make better and better and more efficient engines. So efficiency of heat engines had a great role to play in the understanding of second law of thermodynamics. We specified to you, we already told you that what is the fundamental definition of second law of thermodynamics, that the system and surroundings entropy is continuously increasing. That is one of the statement of the second law of thermodynamics. However, at the same time you will see that has to do with also the efficiency of heat engines. Like it is kind of disconnected, right? In one case I am talking about entropy of the universe and continuously increasing, another case I am talking about that thermodynamics limits the maximum efficiency of any heat engines, and this efficiency of engines drove the foundation of thermodynamical principle. And it started, or the I can say onset of this series of ideas that started with Carnot, Sadi is Carnot, Sadi Carnot, around 1824, where he proposed something called Carnot engine, and he defined that what is the maximum possible value of the efficiency of that engine will be. So, it has to do with engines, right. So, and engines, heat engines can be divided into two parts. One is internal combustion engine, where the combustion happens inside the engine, like car and trucks and all that, which are of two types, like gasoline engine and diesel engine. And there is external combustion engine, where combustion will happen outside the engine, like steam engine. So, combustion will happen, steam will produce, and that steam will now push the piston. And steam engine and Stirling engines are example of external combustion engine. We will talk about these engines later in a little bit more detail, at least schematically. So, these engines drove the quest for efficiency for these engines drove or necessary or gave rise to the second law of foundation of second law of thermodynamics.